Okay, so tell us a little bit more about yourself, Jana, and then go ahead with your talk on human in the loop.
Okay, all right. Yeah, thank you, Bernie. Thank you, everyone. I probably cannot see everyone, but I hope you guys can hear me well. As Bernie mentioned, my name is Jana. I have been with WSU for about 8 years now, and I'm a computer science professor. And I do research and teaching in the areas of artificial intelligence, machine learning, applied to a wide variety of science, engineering, and industrial applications, including security. So the stuff that I'm going to talk about today is about anomaly detection, which is actually a very important tool that is applicable to a wide variety of cybersecurity related problems. Okay. And this is a joint work with my PhD student Rakibul Islam, who just graduated and started as a research scientist with Facebook Research, where he would be using some of these techniques to address content moderation, and cyberbullying and so on and so forth. So basically, whenever there is hate messages and so on, how you can use AI and machine learning tools and anomaly detection algorithms in particular to kind of use a good combination of humans and machines to solve some of those problems. And also, this was a joint work with my postdoc, Shubhamay Das. He is now at a startup as a senior research scientist. And this paper is actually on arXiv. You can go to my webpage and you can find it, probably one of the first publications. The code is also publicly available. It's actually very well used outside. Probably there are more than 1,000 users for this anomaly detection code. And hopefully this paper would appear at Journal of Artificial Intelligence Research in the next few months. It's going through a revision right now. Hopefully it will be out soon. I'm pretty excited about this technology. So let me, before I start jumping into the talk, let me try to motivate you with few applications, right? So let's consider credit card fraud, right? Whenever there was everybody has credit cards, and whenever the credit card company thought that there was a fraudulent transaction, they would write you an email or text you to your mobile phone and say, well, is this you, and was it a valid transaction, right? So now it's good when somebody else is using your credit card to do a transaction, and you can recognize that this is actually a fraud transaction. It's good. But what if you are actually using that credit card? Let's say you went to a different country, let's say Paris, and you are doing the transactions. And for every transaction, either the transaction is denied, and you keep getting basically lots of emails and text messages to confirm whether it is you or not, right? That could be annoying, right? So that's what we are talking about here. So if you have a lot of false alarms, then it weighs the human effort of the human that is involved in the loop. Okay, so that's basically the first application, but this would be a recurring theme in a lot of applications. Similarly, here I'm showing you an ICU patient monitoring system. So here, probably imagine a patient being monitored through a variety of wearable devices. And on the right side, I'm showing you a health personnel who is continuously monitoring basically the signals that are being actually generated from the patient, right? The closest I have ever gotten to something like this was when my wife was delivering our kids, right? And I had no idea how to read those graphs. Thankfully, the nurse kind of helped me understand. But different patients have different things, and only the medical practitioners know. And the issue here is that we have lots of patients, right? But the number of medical professionals who can actually understand these and basically recognize what are anomalous and what are not is kind of limited. So we are limited by those resources. So any place a computer can automatically analyze these form of data that is continuously generated and help the humans, it's great. But again, like I mentioned in the credit card application, if there are lots of false alarms, like, okay, the computer keeps telling that, okay, this patient needs your help, he's, in an abnormal state or whatever, then the medical professional has to run to that patient, right? And if it was a false alarm, then we wasted the human's effort. Okay. So again, that's the point I'm trying to drive home here. And the third application I'm going to talk about is the Android malware, right? So we all use, smartphones, whether it is Apple or Android, and there are apps being built, right? And there are always these malwares that can potentially spy, steal personal information, or make fake calls on your behalf, and so on. There is a whole industry around writing these malwares and trying to kind of detect and fix these malwares, right? So all these companies like McAfee and so on and so forth. And as on the right hand side, I'm basically showing you that the number of malwares are actually growing at a rapid pace, right? So here I'm showing only until 2017, but you can easily project how this graph would look like in 2022, for example, right? So again, the point we are trying to make is that can we detect these malware applications as soon as possible so that they don't do the damage? Okay. And here also, if the anomaly detection algorithm kind of tells you, oh, well, this is an anomalous app, but, actually, if it is a normal app, then, again, your time is not well spent in terms of handling those. So with that motivating applications, let me start talking about the problem that we are going to solve today. So the problem is we have a bunch of data, right? So here, every circle point, you can think about it as one data point. And we give this input to a computer, right? A computer processes this data. And this software needs to label this data by saying, oh, these are all normal data, and only the red colored points are the anomalous points. Okay. So this is what the input and output for an anomaly detection problem would look like. Now, what we are going to talk about in today's talk is about how do we build this algorithm or the tool that would take this input and produces this right output. Okay. So that's going to be the focus of this today's talk. And before talking about any solutions, let's talk about why is this problem interesting, that hopefully you are convinced by now because I talked about a bunch of applications. What is so challenging about this problem? The first challenge is really the number of anomalies are actually a very small fraction of the total amount of data, which makes it's almost like finding a small number of needles in a big haystack. Okay. And it's also a knowledge discovery task which involves humans, because what is anomalous depends on the problem domain or the task that you are involved in. Okay, you cannot make assumptions about what is anomalous. Only the humans who understands the task or the application can only tell what is anomalous. Okay. And the third challenge is that if you flag a lot of false positives underlying every anomaly detection system for cybersecurity or otherwise, there is a human agent that is actually sitting next to that anomaly detection system. And whenever the anomaly detection says that, okay, here we are dealing with an anomalous scenario, the human has to look at and make sure that whether it is anomalous or not. And if it is anomalous, the operator has to do something. Okay. So whenever there was false positive rates, which means that we are wasting the time and the effort of the human analyst that is in the loop. So before I talk about the new work that we are going to talk about, let me quickly summarize the prior work on anomaly detection. And much of the work is actually unsupervised, in a sense that you don't require any labeled data. You don't need to see any training examples of, okay, here is an anomalous point, which is the red point, and here is a normal point, which is basically the green point. You need at least some training examples, and then you can build a model, right? So what unsupervised methods do is that they don't require any of that label data. They would analyze the data, they will make their own assumptions, right? And then they would fit models to basically separate out nominals from the anomalous data. So these can be roughly categorized into 4 approaches. The first approaches are density-based approaches. So here you are basically trying to build a probability distribution, and then you basically says that, okay, whichever data points have low probability, then you would basically say that, okay, these don't come from the regular distribution and these are anomalies, right? And then there are quantile-based methods like one-class SVM and support vector data description. So these kind of try to build a model around one class, and everything that doesn't fit one class is basically anomalous. And then there are these nearest neighbor methods like local outlier factor and so on. But the state-of-the-art algorithms in this unsupervised methods are what is called isolation forest. If you haven't heard about it yet, it's okay. I'm going to describe to you. If there is one method that you're going to apply off the shelf, then this is probably the algorithm that would perform the best in the category of unsupervised methods. Okay, so even though it was developed in 2008, even today people have performed empirical evaluation, and this algorithm kind of works really, really well out of the box. So the one question is that, okay, why? Okay, there are so many unsupervised methods. When and why they may not work in real world scenarios, right? Like I mentioned, every unsupervised method, they don't have any labeled training data for what is nominal and what is anomalous. So they make some model assumptions about what is nominal statistically. And then whenever those modeling assumptions are violated, those methods won't work. And the other challenge is that sometimes the nature and the type of anomalies are not known beforehand. We call this phenomena unknown unknowns. Okay, so for example, unknown is basically which are anomalous, and even within the anomalous set, you might not know which ones you are probably interested in. Okay, and like I mentioned in the third bullet, only a subset of the identified anomalies are probably relevant for the real world task. For example, a cybersecurity application or the credit card fraud detection. And as a result of these 3, whenever any of these scenarios arise, we with the unsupervised methods will result in a high false positive rate. And whenever there is a high false positive rate, for every false positive, the human analyst who is sitting next to the anomaly detection system has to put in some effort, and that's not a good thing to do. Okay, because humans' time is much more valuable. So the key question that we are going to answer today using some of the new algorithms is, can we use the human analyst who is in the loop efficiently to improve or configure the anomaly detection system better? So it's basically we are trying to build a human computer collaborative system where they will work together as a team and and both of them have the common goal that, okay, I want to improve and I want to help you save your time and effort in terms of detecting anomalies accurately and reduce the false positives. Okay. So what happens is it's an iterative loop. The human is in the loop, and every time the algorithm would say basically, okay, this is a candidate that I want to basically know what is the label, and the human analyst looks at it and then produces the feedback, whether it is nominal or anomaly, and then the model gets updated. So it's basically an iterative loop where the anomaly detection system improves based on the feedback given by the analyst. So for example, the analyst can say certain instance is nominal or certain instance is anomalous. Okay. This is also related to the other learning paradigm. So there are 2 kinds of learning paradigms in machine learning. One is called supervised machine learning, where you provide a bunch of training examples for any task that you want to automate. And then you build a model, and then you go and make predictions on unseen examples, right? The second kind of learning paradigm is what is called active learning, where rather than teacher giving you a bunch of question and answer pairs, now the student gets to actively ask questions. Okay, so here the assumption is that the teacher's time is very valuable and you want to ask the most informative questions, not the dumb questions that would increase your knowledge the most. So here I'm showing an illustration. So it says nominal, and then the model gets updated, and then you have one labeled example, and then you have another label. Now you again ask the human analyst. The human analyst says it's an anomaly. It gets added to your training data. You update your model, and so on and so forth. So our overall goal through this process is we want to discover as many anomalies as possible, right? So these are, remember, the green refers to the nominal points and the red refers to the anomalous points. And we want to discover these red points as quickly as possible with the minimal number of queries being posed to the human analyst, okay? Which basically means you're reducing the false positive rate and you're minimizing the human effort, okay? So there are a bunch of questions that we need to answer. One is, what is this model going to be and how is it initialized? And in each iteration, which example we want to query? And once we get the feedback, how do you update the model weights? These are the three main questions, okay? So before we talk about it, let's talk about the isolation forest, which is the underlying algorithm we are going to use because this is the best algorithm. And it makes sense for us to improve the best algorithm to improve its performance, right? So the key idea behind isolation tree is that the anomalies can be easily isolated from nominals. So you can think about, you are kind of partitioning the entire input space. So think about your points being lying on a Euclidean space, right? And you are partitioning this input space into a bunch of rectangles or hyperrectangles, right? And think about this as a hierarchical representation where you have big hyperrectangles at the top and the smaller hyperrectangles at the bottom, and so on and so forth. Okay. So when this happens, the points can belong to any of these subspaces. And what you are trying to kind of say is that if an anomaly, anomalies can be separated very easily, which means that the anomalous examples will be at the smaller depth and nominals will be at a larger depth. Okay, so here is an example. So what you do is that this is kind of a decision tree if you have heard about it, but if you haven't heard, that's okay. All you have to do is basically in each iteration, you would pick randomly a feature, randomly a split point, and then you would decide, okay, whether the point goes to the left or to the right, and you keep repeating it, okay? And what is it called? This is the square, right? So the square basically corresponds to the comparison operation. So which feature is involved and which split point. And the ovals, whether it is colored or not, refers to leaves. Okay. So if a point belongs to a shallow leaf, that means that it's likely going to be anomalous. And if a point is actually in the larger depth, then it's going to be nominal. So as you can see, I'm showing you a color-coded tree depth, right? So if it is more blue, which means it's nominal, and if it is more red, it is going to be anomalous, and in between there is a varying trade-offs. So this is the partition subspace I was talking about. So this is a two-dimensional space, and you can see that here we have a bunch of rectangles that are separating out the points, okay? And if you look at the depth colored subspaces, it basically says that the points on the lower left corner and the top right corner, these are the anomalous, and most of the center region is kind of nominals, okay? And this is basically for one tree, okay? So the score of a node is a function of the path length. For now, just assume that if the path length is small, then it's going to be more anomalous. And if the path length is large, then it's going to be more normal. Okay, and that's what this color coding is showing you. Now, a forest basically means a bunch of trees, right? So all we have to do is we have a bunch of trees, and you get basically your forest. And any data point that you have, you would basically pass through each of the tree and you would get scores, and then you combine them. to compute the anomaly score. So this is a state-of-the-art unsupervised approach, and the assumption it makes is that the number of anomalies are small, which in practice actually it is, and the features are distinguishable, which basically means that the features provide you some information to separate out nominals from the anomalies. The main issue with isolation forest is that it assigns uniform weights for subspace scores. Okay, so if you see, every leaf corresponds to a subspace, and it assigns equal weight to every subspace here, and that's probably the problematic part. So again, here I'm showing you the random forest with the space partition for 100 trees, and each color corresponds to one tree. And now you can see one tree versus the full forest. The center part, now you can see the regions of nominal versus anomalies much more clearer, in a sense that the anomalies are concentrated around the four corners of the square, and the nominals are centered around the center of the square. Okay, so this gives you a much more accurate representation compared to a single tree. So the point I'm trying to make here is that a forest is better at anomaly detection compared to a single tree. Okay, so the ensemble kind of helps you. So now remember, there are three questions that I mentioned. One is, how do you initialize? What is your model? How do you initialize the model? And how do you ask questions in each iteration? And once you get answer from the human analyst, how would you update the model? Okay, so the forest, as I mentioned, has a lot of leaves. Every leaf becomes basically one feature value in this representation. Okay, so you take every leaf, correspondingly there would be a value. Okay, and then let's say there are m leaves, then this would be an m representation that corresponds to m values. Okay, and we are assigning equal weights to these scores to begin with. Okay, and one of the things that we have figured out was that assigning equal weights or uniform weights actually makes a lot more sense in the context of isolation forest, and that's one reason it works really well, because the optimal weight deviates from the uniform weights by a very small angle, which basically means that you only require a small amount of labeled data to go from the uniform weights to the optimal weights, which actually helps in terms of the sample efficiency or the data efficiency to discover your anomalies. So what we do is that every data point, we pass through basically all the trees, the isolation trees, and you get your representation. And then the W corresponds to the uniform weights at the beginning, and then you multiply all of them, and then you get basically a score. Okay, and then every data point gets a score, which is the anomaly score, and then you rank all these data points according to those anomaly scores, and you pick the top tau fraction of the candidates as anomalies. Okay, so if your weights are really good, right, and then most likely most of the top tau candidates are going to be anomalous. But if your weights are not, then maybe you will have false positives, and that's what we are trying to fix. Okay, so the question really is that how can we learn the optimal weights? So this is basically the high-level overview. So this is basically your anomaly detection algorithm, where you have your models and the weights and the scoring function is sitting. And here is a bunch of labeled data and unlabeled data that is existing at any point of the algorithm. And in each iteration, what happens is, in each iteration, what happens is you pick one labeled, unlabeled instance for feedback, pass to the human analyst, and the human analyst analyzes the data and says whether, well, it's a nominal, then it becomes a green point. If it's anomaly, it becomes a red point, gets added to the labeled data, and then your model gets updated. And during this process, sometimes, right, the human analyst would also want to understand, okay, why the heck basically this anomaly detection system is asking me to verify or provide feedback on this particular input, right? So you need some kind of interpretation or explanation that actually helps you. So for example, we are trying to kind of detect nominal versus anomalous loan applications in a bank. Okay, So then a potential interpretation is that, well, you give the loan application to the loan manager here, and the anomaly detection system says that, well, this applicant has a credit score who is low and he's not employed, he or she is not employed. That provides a little bit more context to the human analyst about understanding what exactly the anomaly detection understands and what it doesn't. Okay, so explanations and interpretations are kind of very important things, mainly for the any data analysis systems. So the point here is that we want to use human feedback to improve the anomaly detection performance. So what we do is, so every time you have the highest scoring unlabeled example, right? And then you ask that as basically your input. So for example, here you have this point and you ask basically the human analyst for feedback, and you keep doing that. Okay, so every time you get example, you keep doing it, you update your weights. So it turns out that the greedily selecting the highest scoring unlabeled example is a very good querying strategy, partly because of the way the weights are initialized to uniform weights in the context of the isolation forest. Okay, there's a little bit of technicality here, but I'm not going to go into that detail for the sake of ease of understanding. So the question is that sometimes we might have data where there are basically different types of anomalies. Okay, anomalies of certain type, anomalies of type B, anomalies of type C, and so on and so forth. Now what happens is, if the model kind of identifies one class of anomalies, then it might actually keep giving or identifying only that class of anomalies, not the other ones. Whereas from a real world perspective, it makes sense for us to discover as many anomalies as possible from different types or classes. So you need some diversity in your anomalies. Okay, so actually we can use the isolation forest's inherent structure to actually do this diverse selection. So for example, think about, these are all the candidate regions, and if you only select from the top, you're going to select all the points from the same region. But if you do the diverse selection, then you actually select points from different subspaces. Okay, so there is a way to do that, and we have a concept called compact subspaces. So we take all the subspaces and then they try to identify a small set of subspaces that covers all the labeled examples so far. Okay, it's related to set covering problem. And then if we want to discover diverse anomalies, all we have to do is we have to pick subspaces that are diverse enough and pick basically queries from them. Now, so far what we have talked about is how do we initialize the model, how do we query the points, whether it is only a single query or a subset of the queries when it comes to diverse anomalies. But once you get the feedback, you need to update your model, which is the weights of each of the leaf. Okay, so we want to learn weights so that the anomalies are ranked higher than nominals. I mean, this is by definition, right? We want the score of the anomalies data points to be higher than the nominal data points. So, and we know that the score of any data point is weights multiplied by the feature representation in the subspace. Okay, so you can think about this as a bunch of ranking constraints, and you have your old weights and label data, and you have new label data, and you have to produce new weights that satisfies the ranking constraints, right? So after the feedback, you want the nominals to be ranked lower than the topmost tau fraction, and you only need a small change in the weights to satisfy the constraints, because at any point of time you are getting maybe one labeled example or maybe few labeled examples if you are querying in a batch. So let's say here is basically an illustration. So here is the current scoring of the data points according to the current weights at a particular instance of the time. Okay, so here the red points and the green points are the current labeled examples, and the gray colored points are unlabeled. We don't know whether they are nominal or unlabeled, nominal or anomalous. And in each iteration, remember, we ask basically the highest scoring labeled example, unlabeled example for query. Okay. So now we ask basically the unlabeled example for scoring, and then it says nominal. So now we update the weights such that the score of this point is actually below this quantile. Okay, the top 12 quantile. And you keep repeating that. Now again, you have an unlabeled example. You don't know the label. You ask the human says anomalous, and now that anomalous point actually should be ranked at the top, in the top tau fraction, and you keep repeating that. Okay. So now this is a good time to know basically that, okay, now that we know the approach, how it works, does it work well, right? So we have the unsupervised approach where basically you don't use any feedback at all. And then we have the human in the loop anomaly detection algorithm with few configurations like, okay, how do you initialize the weights? Okay, in some cases you have these random weights, and in other cases you have the uniform weights. And one of the things that I told you so far is that uniform initialization actually works really well because the angle between the uniform weights and the optimal weights is very small, which basically means that you need only a small number of labeled examples for your weights to move towards the optimal weights. Okay. So now one thing that we want to understand is that, like, okay, we have an algorithm. How do we know whether it works better or not? So the way we can measure is we see as a fraction of the number of queries or feedback queries that we asked the human analyst, how many of them corresponded to the real anomalies. Okay. So if the fraction of the anomalies out of the total number of queries is high, then basically we say that the algorithm is performing well. So here I have 3 representative data sets for anomaly detection. On x-axis, I have the number of queries or the data labeled instances. On y-axis, I have the fraction of the total anomalies seen. Okay, so here you are basically saying out of the 50 examples that I have labeled, what fraction are actually anomalous. Okay. And one good thing that you can see is that as the number of labeled examples are increasing, all the algorithms, the fraction of the anomalies seen are also increasing, which is a good thing. I mean, that is what you would expect. Now, the only question is that which algorithms are actually performing at a much higher rate. Okay, that means that smaller the number of queries and still your anomaly detection rate is very high. So as you can see, all the algorithms which use feedback of the human actually perform better than the algorithm that doesn't use any feedback. Okay, so which basically means that the human feedback played a very important role in discovering more anomalies. Now, the second point I mentioned was, what if I was interested in discovering diverse anomalies? Okay, so let's say you have now anomalies from different classes, and if you are using diversified querying, right, from the diverse subspaces, as you can see, sorry, my bad. You know, on the x-axis, I have the number of batches from the start. So every round you actually ask 3 queries. And on y-axis, you have the average difference in the number of unique classes per batch. Higher the better. And as you can see, the diversified querying actually does significantly better, right? So it discovers diverse anomalies in all the data sets. And it does so without sacrificing the anomaly detection performance overall. Okay, so you're not losing anything. You're getting basically the same anomaly detection performance if you ignore completely the different types of anomalies. But because of this diversified querying, you're able to actually discover diverse anomalies. Now, so far, what I talked about was all the data is actually sitting on your hard disk or in your memory, and you have to analyze and figure out which ones are actually anomalous and which ones are nominal. But in a lot of real-world applications, including cybersecurity, the data is arriving at a very, very fast rate. Okay, you cannot store the data, And you need to process, analyze this data as the data comes in and detect which ones are anomalous. Okay. So identify anomalies from the continuous stream of data. So for example, okay, at time t1, you have this data and then new data arrived and then new data arrived as the time window moves. And we want to find still the same problem. It's just that the data is coming in an online manner. You don't have access to the entire data. So what are the challenges when you move from the static data to streaming data? One thing that we need to figure out is that, well, is there any concept drift, which means that what was anomalous 1 month back may not be anomalous today, right? Because that concept is changing of what is anomalous versus what is nominal. And again, the same question of when and how to update the model. And if you have memory constraints to store data, how do you handle? Okay. So think about if you have a network traffic and you are trying to solve a network security problem, the data is probably coming at several megabytes per second. You cannot store all of that in a hard disk or in your main memory. Okay. So in those cases, you have to make some design choices about which part of the data you want to store in your memory so that it helps your overall data analysis towards the security problem that you're trying to solve. So here is the illustration of how streaming anomaly detection is done. So you have all this data, right? So you build your isolation forest, again, a bunch of trees, and then you keep asking queries and you get a bunch of labeled examples and you get your new data in time t2, and then you build some trees, and then you again ask for feedback and try to discover anomalies, and you keep doing that. Okay. So the only thing is that, okay, should you keep the trees as it is fixed throughout the process, or you should change? If you want to change, how do you decide when to change and what to change? Okay, so those are the main questions that we need to answer. So we have this concept called drift detection. So what happens is that if you think about any data and a bunch of trees that are available, what you do is that you basically kind of find how many leaves, how many data points are there in each leaf. If you can kind of count them for a bunch of trees, then given two sets of data, you can actually compare those counts and see how much they differ. If they look very, very similar, then you probably there is not much change in the data and you can live with your current trees. But if actually the data changed, then which data points go to which leaves might change. And we actually compare this data distribution using a statistical metric called KL divergence. Okay. If the KL divergence is very high, that means that these data distributions differ quite significantly, which means that your old models that you have for the old data might not be applicable to the new data, and you have to update your models. Okay, that's what it is saying. So in this case, there is not much drift that was observed, but there are other problems like this where there is a lot of drift that is detected. Okay. So we have two scenarios. One is we have limited memory in all cases. In a lot of real world applications, you cannot store all the data, right? And we have minor concept drift, which means that the concept actually doesn't change too much. It's only a minor epsilon change. But the second scenario, which is the hard part, is you have a major concept drift. In this case, the model or the trees that you have may not represent the new data, which means you have to replace a fraction of the old trees with the new trees built on the new data. Okay. And then you initialize the weights for the new trees with the default, which is the uniform weights, which we know that it works really well because the angle between the uniform weights and the optimal weights is very small, and it helps with the active learning. So again, we actually set up the streaming algorithm the way we have talked about. And now one question you could ask is that, when you have the entire data and you are running the algorithm, you have the advantage of hindsight. But when the data is really in a streaming scenario, you don't have the luxury of the hindsight. You have to deal with what you have, right? So always the scenario where all the data is stored and you're doing the analysis is going to be an upper bound for a streaming algorithm, because there will be some loss in performance because you don't have the luxury of the hindsight. So here, the first set I'm showing you is the no drift scenario. And basically what it shows is on the x-axis, you have the number of instances labeled. These are again the same number of queries you're asking. And on y-axis, you have the fraction of the total anomalies seen. Higher the better. Okay. So with feedback, of course, the highlight batch is consistently the best performer because you would expect that, right? A streaming algorithm cannot compete with a static algorithm. But the streaming algorithm is almost very close to the static setting, which basically means that our streaming algorithm was pretty good in making predictions and placing its bets. Now, if you have concept drift, like I mentioned, that means that your data has changed, which means that you have to change your model also. So in this case, you can replace a bunch of existing trees with some new trees. The only question is that what fraction you should replace, right? So it turns out that we have done a lot of experiments around this number of trees, and it turns out that 20% trees replacement works really, really well and is stable across a lot of data sets. Okay. Again, here we use this, KL divergence and decides basically how to automatically decide when you want to update the model, and you use basically 20% of the trees to be replaced. So first you need to ask whether there is a drift or not, right? And that's what your KL would actually tell you. And once you have detected there is a drift, then you automatically replace 20% of the trees, which worked really well across a lot of problems. So which brings us to the summary of this talk. So I'm motivated why anomaly detection is a very important tool for a variety of cybersecurity applications. Even though I talked about only 3 applications, there are a whole bunch of cybersecurity applications where you can deploy anomaly detection. And I talked about the challenges for anomaly detection, which is the number of anomalies are very small compared to nominals, right? And a lot of the times we don't know what anomalies are, and they depend on the context, and only the domain expert can actually know which are anomalous and which are not. And existing unsupervised methods like isolation forest, which is the state-of-the-art algorithm in that space, they make certain assumptions about what is nominal and anomalous. And whenever those assumptions violate, what happens is you get high false positive rate, and which means that the human analyst who is using the anomaly detection system has to take certain actions, is wasting the human analyst effort. So what I try to show you is that the human and the computer can work together as a collaborative team, where the overall goal is for the human is to improve the anomaly detection system's performance or configure it as needed for the domain, so that the number of false positives gets reduced over time and the system becomes really accurate, because this is in the best interest of the human analyst. Because once the system is actually becomes very accurate, then the human analyst effort would be minimized. Okay, so we talked about a bunch of algorithms to kind of tune these ensembles or the unsupervised ensembles to reduce the false positives. And we exploited the structure of the isolation forest to discover diverse anomalies. Remember, we have this compact subspaces concept, and we tried to query from different subspaces. And then for handling streaming data, which is actually very natural in a lot of cybersecurity applications, we try to detect the drift, which basically says that, okay, I look at my current data with the old data and see how much they differ. And if they differ by a lot, then I have to update my model, and then I have to update the weights of the models as well. And we have seen that human feedback significantly helps in reducing the number of false positives and significantly improves the detection of anomalies. So with that, I would like to conclude my talk, and I am open to taking questions, and hopefully you guys learned something useful today.
Questions? Okay, got a question here, Richard.
Has anyone considered taking accurate isolation trees, separate ones, separate tests, and running them against each other to find correlations that have never been considered before? Is there any interest in that type of study?
I'm not able to hear or understand the question. Can somebody type in the chat if it is easier?
Can you hear me now?
I can hear, but there is a lot of noise, Bernie.
Go ahead and stand by that.
Yeah, if you can come to the podium or wherever Bernie was speaking, I think that was better. So, I mean, yeah, if that is easier.
Okay, I'm getting the microphone. Yeah, so we're, okay. Go ahead.
I was curious about any interest in taking isolation tree studies that are highly accurate in different areas and combining them to find new correlations that have never been considered.
Yes, I lost you guys at the end. Can somebody can somebody type it? It would be easier.
Can you hear me now?
Yeah, exactly. I can hear you now. Please go ahead.
Okay, so I was curious about taking different isolation trees with a high degree of accuracy from totally different studies and combining them together to find new correlations between them. If there's any interest in that, if that's being done.
Yeah, I think it's a good question, but I think it's been studied in a sense that when you are building these isolation forests, you are making these random decisions, right? I mean, you take the random features and random splits. You can think about the way you are trying to interpret is okay. If I have one view of the problem, right? I have isolation forests or trees associated with that view. I have a different view of the problem or different kind of data, right? So maybe, let's say, for example, we have sound data, we have image data, we have video data, we have sensor data. And then we are building isolation trees for each of that modality. And then we can combine all the views because it makes sense. Because when we want to really detect these anomalies, we want to be able to use all the modalities or all the views that would actually help us make better decisions. So that's a great point.
Thank you.
Other questions? So this could be any kind of data. Let's say we had a sensor for, like in my field, a bioreactor or a chemical reactor that's taking concentration data or maybe oxygen level data or something like that, something from a sensor.
Mm-hmm.
That could be used in this type of approach. I mean, this type of approach would apply to that. Okay.
Yes.
I didn't know if it was like algorithmic data, but it sounds like it could be anything.
Yes.
Very good. Any other questions? Okay, let's give our speaker a big hand.
Everyone, thank you for hosting me.